Hey guys, welcome back to another episode of Simuleos. Today we're going to be working on something a little bit different. So, yesterday we kind of sort of did the DMRG stuff and there was a bug in it. That said, I did not have time to debug the bug, but I did have time to look up some Huffman stuff. Now, the reason I didn't quite finish debugging the DMRG stuff is because there are actually people at OIST who are really good with spins and anything to do with what we dealt with yesterday with DMRG. So I said to myself, hey, why don't I wait until I can talk to one of these people, and then we'll get back started with DMRG, because they probably have a good idea of what I need to do there. On top of that, yesterday something kind of big happened on my YouTube channel, and I'm actually really excited about this. So my last video, I guess I'll go to my channel over here. My last video has over 8,000 views, which is really good for a channel that only has 700 subscribers, which is really good for a channel that had 482 subscribers 2 days ago. So I got, let me see, 482 plus 225 extra subscribers on YouTube, which is crazy for me. And I just wanted to point out that that is actually really cool and gives me a lot of motivation to, oops, sorry about that. I don't know why I have Nightbot up. It gives me a lot of motivation to do new projects in the future, and I have one that involves Huffman encoding, and I really want to see how this one works out, because I think it could lead to a really cool visualization. Now, the problem is, this last video that I made was about eigenvectors, and, you know, everyone has questions about eigenvectors. It's one of those things that is very difficult to understand intuitively, right? So a lot of people ask a lot of questions about eigenvectors. So the way I see it, the reason people were watching that last video was because, how do I put it? Was because there were a lot of people who had a lot of questions about it, you know? It was kind of like a tutorial video in a way, like, what is this type of thing? Which is fair enough. But my upcoming videos I don't think are necessarily going to be tutorial videos. Sure, there will be a few things that I'm going to explain that people will definitely have questions on. I'm thinking about doing one on Taylor expansions and stuff like that. But for the most part, I would like to start doing things that are kind of, I don't know, I still want to teach things, but I also want them to be things that are not always on the path everyone, you know, goes on, you know? So everyone encounters eigenvectors, right? So that's the simple one. But Huffman encoding is one of those things that not everyone hits, but I think is super cool anyway. So with Huffman encoding, what I want to do is I want to start today with basic Huffman encoding and see if I can visualize it in the way that I want, which might come tomorrow or the day after that. I'm going to be using the same code that I've been using to draw the subroutine webcomic for this, so hopefully I can get videos and stuff working on that soon enough. We'll see how that goes. Hey, iCare, thanks for coming in, and Gusterin too. So, what are we doing today? Well, today we're going to draw a basic Huffman tree. Nothing fancy. It shouldn't take that long. And then I want to see about visualizing it. And that's going to take a few days, because I need to make sure it's just right, it looks good, everything like that. Then, after that, we're going to come back to this, and we're going to... Sorry about that. Draw adaptive Huffman trees using the Vitter algorithm. Now, the Vitter algorithm, when it comes to adaptive Huffman encoding, for the most part, you've got a choice between two different algorithms for adaptive encoding. You've got Huffman, the adaptive Huffman encoding, and then you've got the LZW, I think is what it is, and that is the, I don't remember what it stands for, but it is another algorithm invented by another group of people, and this algorithm, let me see. Nope, that's Linslaw's iteration. 1 second, I can't seem to... I know where I can find it. 1 second. Yeah, LZW. So the LZW algorithm is used most frequently with adaptive encoding, but since we already have a Huffman thing going on, I figure, hey, let's do adaptive Huffman. We could also do LZW a little bit later. There's like no time restrictions here. In terms of videos that I have ready to go, we could do a video on quantum Monte Carlo, we could do one on ray optics, optimal control, finite difference, one on OIST if you guys are interested, or Monte Carlo stuff coming up. We could also do one on Taylor series. We have a lot of things we could do videos on. And I'm going to try to make a video every 2 weeks, I think, is going to be my production schedule. So this weekend I got to do some filming. So depending on how this Huffman stuff goes today, I may or may not do filming on it this weekend. So we'll see how it goes. Anyway, let's go ahead and get started. Opening up Zernal and going from there. Zernal. Okay, so first of all, what is Huffman encoding? That's the question. Now here's the thing. I learned Huffman encoding from a math professor. A lot of people learn Huffman encoding from a computer science professor. So the way that I do Huffman encoding might look a little different, but the end goal is all the same. So first of all, Huffman encoding. Encoding. Okay, so Huffman encoding. What is the general idea? The general idea is that we have some sort of string. I don't know, I just abab. That's a string. And we want to convert it to a whole bunch of bits. So maybe 1, 0, 1, 1, 1, 0, 1, 0, 0, or something like that. That might be a good bit where A is going to be 1, B is going to be 0, 1, and C is going to be 0, 0. That seems fair enough. Now, in choosing these codes, we have to follow a couple of restraints, and I guess we'll go into the restraints first. So let's take a look at this. New page before. I'm gonna create a random string. You guys feel free to give me random strings because I will probably need to have a few random strings throughout the course of this. So if you guys have any suggestions of strings you want me to try, let me know. For now, I'm just gonna do a simple string of hello. Okay, so that's my string. It has 4 letters in it, H, E, L, L, and O. So let's just randomly map these guys onto different things. Okay, so we're gonna do H, E, L, and O. And we're gonna say, and this is just a random map now, just we're pretending things are things. So let's do, I don't know, there's 4 of them, so how about 1, 0, 0, 1, 0, 0, and 1, 1. Okay, so that means after encoding, we have, let me see, so we have, let's see, 1, 0, then we have 0, 1, then we have 0, 0, 0, 0, 1, 1. Okay, that's fine. Now this one's kind of sort of easy to decode because we know that every single one of these guys is 2 characters long. And that's fine. These are all kind of unique. And they're all what's called prefix free. Let me put it that way. Okay, so when we say prefix free, we basically mean that there is H, for example, is not held within E, and L is not held. Writing them out of order hurts my poor. Wait, what do you mean writing out of order? Sorry if I'm doing it out. I don't know what you mean by out of order. Again, I learned this from a math professor, so forgive me if my notation's a little bit different. Okay. Now. Oh, you mean L should be first. Yeah, L should be first, but I'm just kind of working from what people might do if they want to encode things. So first of all, this particular code is prefix free. Oh, yeah, sorry about that. That I also did. Okay. So by this I mean H is not held with an E, E is not held with an L, L is not held with an O. Sorry, my bad. Okay. So, we need to think of a better way to hold these digits though, because in this way, H, E, L, and O are all 2 digits big, but L is used twice, right? So we could think of a way potentially where L is only 1 bit, and this would save us 2 bits in the end, right? And the idea is to minimize the number of bits. So let's think about this again. What if L was instead of 0, 0, just 0? Okay. Well, in this case, we'd encode everything as 1, 0, 0, 1. Then we would do, let me think, 0, 0, 1, 1. Okay. Sure, that seems like a reasonable string. Now let's try decoding it. So H right here is 1, 0. That seems fine. This one's going to be an L. So we have H. Then we have L, because 0. Then we have 1, 0 again, so now we have H again. H. Then we have, well, it looks like another L. And then we have 0. So our hello has turned into a hello. And that's kind of the idea, right? If we have something that is not prefix free, as an L is a prefix in another letter here. Oh, sorry. Then it becomes hard to decode with what's known as a greedy algorithm. Wow, I cannot write today. Greedy algorithm. So, now again, this notation's a little weird and is a few years old, so forgive me if I'm a little rusty here. So anyway, the greedy algorithms are algorithms in which they do not look ahead. They just pull whatever letter they see first, and they just say, okay, 1, 0, that's a letter. 0, that's a letter. 1, 0, that's a letter. And they don't worry about looking ahead or anything like that. So prefix-free code makes it easier to decode. Okay, so now let's talk about how to create these codes. I'm going to create another random string, and this string is going to be, let's say A, B, C, A, B. Okay, that's my string. Okay, so let's pretend you're on the phone, and someone's just giving you random strings, right? They're just continually giving you letters over and over and over again. And let's say, just by pure chance, they give you an A 60% of the time. So there's a point, or let's say 50% of the time, 0.5% chance of getting an A. Okay? And let's say B's come in, I don't know, let's say 20% of the time. You can decode all the variations. This case is actually just impossible to decode since it's ambiguous. Yeah, that's exactly what I was saying before. You can decode all the variations, but that doesn't help you too much. Yes, that's also fair. Okay, so wait, let me do this again. So A comes in 50% of the time. B comes in, wait 1 second. 2 divided by 6, so B comes in, let's see, 33% of the time. Is that right? 2 divided by 6 is going to be 1/3. So this comes in 0.33% of the time. And then C comes in 1/6 of the time, which is going to be 0.17. Okay? So this is just kind of the frequency at which you've received these letters in here. Now we might ask ourselves, how do we create a good code to decode with? One way is by using the Huffman algorithm. Now the Huffman algorithm is kind of sort of a simple thing to think about it. Oh, okay, yeah, fair enough. Okay, so let's go here. And Gustorn is right. There is not really a well-known algorithm to use the code that I used. The one that I had in the previous page is, as Gustorn said, it's ambiguous. You can't really use that. But I wanted to kind of throw the word greedy in there because greedy is a fun word. Okay, so what we do is we take the lowest two, B and C, the smallest valued ones, and we add them together to 0.5. 1 second. 5. Okay. Now we add the next lowest two, which happens to be these two, and we do again adding them together for 1. Now, how you notate this is different depending on how you learned it. I learned it from top bottom, some people learn from left right, doesn't matter. As long as you do 1 0 1 0, you put 1 on one branch, 0 on the other branch, you can create the code that you want. So in this case, A is going to be 1. B is going to be 0 1. So we go 0 1, and C is going to be 0 0. Yes, and this will create a prefix, or this will create the code that you want. Now, if you read from the other direction, let's say you accidentally read from the other direction, B would be the only one that's changed, and it's 1 0, which is obviously wrong because this would be decoded as A first, right? So you can kind of, if you ever have to do a sanity check there, just try decoding the other direction and see if it makes sense. That's the point there. So this is a very simple algorithm, right? All we do is we add the two lowest and then add the two lowest again. We always add the two lowest. But let's get a more complicated frequency of points. So let's say we have A, B, C, D, E. Okay? And we're going to say A comes in with a frequency of 0.4. B comes in with a frequency of 0. I don't know, 2. C comes in with a frequency of 0.2. Let me see. D comes in with a frequency of, what is this added together? So that's 6. Wait a minute. That's 4. So D comes in with 0.1. E comes in with 0.1. So these all have to add up to, what is it? They all have to add up to 1 in the end. So what I'm actually going to do is I'm actually going to say these are 0.15, 15, 15, 15. So they all come in with equal frequency down here. Now this is something you have to kind of pay attention to, because in this case these two will add together to 0.3, but now these two are the next lowest, so they add into 0.3. These two again are the next lowest, so they add into 0.6, and then these guys add in to 1. So when this is decoded, 1 0 1 0 1 0 1 0, we have A as 1, B as 0 1 1, C as 0 1 0, D as 0 0 1, and E as 0 0 0. Okay? So that's how we decode this one. You'll note that A has only 1 digit, whereas everything else has 3. And that's because A comes in so much more frequently than everything else. The nice thing about the Huffman encoding scheme is that it's intuitively simple. You know, you kind of get the idea. You add in the small, you always continually add in the smallest values. Now, in terms of terminology's sake, just to point this out, A, B, C, D, E, these guys are typically called leaves, and this guy is typically called the root or trunk or whatever you want to call it. But basically, this is usually called the root, and this is called the leaves over here. The Huffman trees are different than typical trees in that they're always built from leaves down, and you always add the lowest values, so the smallest values, together first. So the idea is that you will create the tree, but it might create different branches like we've created here. And it always depends on the frequency in which you have A, B, C, D, and E. Now, just for the record, this can be done in a number of ways. There is, for example, this idea of adaptive Huffman encoding, which we'll talk about a little bit later. But for now, let's just kind of point out the idea. So with Huffman encoding, let's say you have a huge string of a lot of letters. So I don't know, A, B, A, B, C, C, D, A, B, Q, A, B. Okay, I don't know who's sending this string, but someone's drunk. Is a drunk text. You know, I send a lot of A's during drunk texts, so yeah, that probably makes sense. Okay, so let's say you get a string like this. In Huffman encoding, you could imagine that this was just a random string of values that you were given. And then you could go through and you could say, okay, well, this means we have A with a particular frequency. So let's see, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Let's remove that one. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of 16 are A's. 1, 2, 3 out of 16 are B's. Let's see, 1 out of 16 are D's. And let's see, 1 out of 16 are Q's. Does this add up? No, it does not. 1, 2, 3, 4, 5, 6. Oh, I forgot the C's. 2 out of 16 are C's. So A, B, C, D, Q. Okay? So in this case, what you needed to do first was go through and pass through the entire string, right? And in that string, you got your frequency, and then you can encode everything based on that frequency, right? And that's fine. That's a good way to do it. However, there are ways to do it with only one pass, and these are with adaptive algorithms. Now, the adaptive algorithms, again, we're going to go into later, but I figured I should just prompt the idea right now. By going through with 2 passes, you have to first go through all of the code once, which means you're not decoding or encoding, rather, in real time. And that is kind of a pain, right? Because if you want to do the encoding, chances are you need to do it quickly, or you need to do it in real time for one reason or another. Now, of course, there are, by now, plenty of ways to do things faster than adaptive Huffman encoding. But, as I said before at the very start, since we're working with Huffman encoding now, and I think Huffman encoding will lead to a pretty cool visualization, I want to try doing adaptive Huffman encoding after this, depending on how cool the visualization is. One last thing, guys, I do want to ask your question on, or ask your opinion on. Because the Simuleo's Twitch channel is kind of like where I'm going to start doing all the simulations for my YouTube channel, as I've kind of been mentioning before, and I wanted to stick to a 2-week schedule. I guess I've got a question of, is there anything that you guys in particular would like to see in a YouTube video? Because I know you guys aren't necessarily the YouTube crowd. You guys are more or less the Twitch crowd, which is potentially a different crowd. But if you have a video or something, like maybe a tutorial or something you want to see done, maybe not a tutorial, but something that you think could be described better, let me know, and I can totally write that down as a potential future video. So I got a couple new ideas after posting that last video, and now I'm kind of going through and seeing what else we have. What I want to do, if I were to go into a cryptography one, which I think would be a really cool video, I'd like to do some encoding and decoding first. So this Huffman stuff would eventually lead into cryptography, which would lead into the quantum cryptography, which comes from the quantum information stuff we did before. So it all kind of builds on itself, you know? And that's kind of the neat thing, I think, about a lot of the simulations we've done. They do kind of build on themselves. So there's a lot of things that we could do here. And I don't necessarily want to make all the videos like 2 or 3 parters, and I don't want to necessarily say, hey, look at these previous videos. But I do think it's fair enough to reference those previous videos while we're making the videos. Let me see. While I'm making the new videos. So like, for example, if I do one on what Lagrangians are, I would definitely like go back and say, hey, look, eigenvectors are incredibly important in this case. Or, you know, certain things like that. Oh, you know what? What is it? The Lagrange multiplier method actually is something that I should really write down. 1 second. And then I also least action. We could also calculate entropy for fun. Yeah, actually, that would be a lot of fun. There's a lot of things. So the thing is, I only think about certain things, you know, because I'm one guy. But I find it really interesting because, like, I'd never gotten suggestions of things to put on my YouTube channel before, so I never really thought about it. But if you guys have something that you want to see, it doesn't have to be for YouTube. It could be just on Twitch. Let me know. Because a lot of times things that happen on Twitch end up being cool enough that I want to put them on my YouTube video. So things like that. Anyway, with the encoding here, all we have to do is the same thing we did before. And again, this is just motivating what we're going to do in the future. Instead of taking, let's say, so for this, we do the same thing we did before. We just add these guys together. So these guys are added first to 2/16. Then these guys are added next to 4/16. Oop, that was a 6. These guys are added next to, what is this going to be? It's going to be 7/16. And then these guys are added together for 1. So we have 1 0 1 0 1 0 1 0. And so A is going to be 1. B is going to be 0 1. C is going to be 0 0 1. D is going to be, let me see, 0 0 0 1. And then Q is going to be 0 0 0 0 1 2 3 4. Okay, and so that's kind of the idea, right? We've taken A, B, C, D, E, or A, B, C, D, Q, and we've encoded them. But now let's think about something else. What if, new page before, we did the same string we did before, A, B, I think there were 3 A's next, dang it, A, B, C, C, A, B, C, C, D, then I think it's A, B, Q, B, Q, I think it was 2 A's at the end. Oh, 3 A's. A. Okay, that's what we got. So let's say we take the same string and we do something different. So we create a whole bunch of different trees. We say, okay, well, we're going to create a number of trees that is dependent on how many A, B, C's and we have so far. So we start here, and A is going to be basically 1, right? Because that's our first tree. Pretty simple. Now we have A and B, both of which occur with a frequency of 1. So A1, B1. We add these guys together, and now we have A as 1, B as 0. So we're encoding as 1, 0. This is just kind of a rough estimate. There are obviously, when we get into the algorithm itself, you will see that it is different than this. This is just kind of the idea. So now we're on A, B, A, right? So now we have A of 2, B of 1, and these are added again to 1, 0, so A is 1. Now, this remains the same for the next 3 or 4 of them. In fact, it remains the same for a lot of them. So then here we have A of 3, here we have A of 4, and all of them remain the same, so the tree doesn't change, 1, 1. Next we have B again. B has now changed to 2, but the tree remains the same, so this is a 0. Now, the next one we add a C, so it goes A4, B2, C1, and this one changes. So now we have 1, 0, 1, 0, and this C is going to be a 0, 0, and this C is going to be a 0, 0, so on and so forth. So basically we just go through and we recreate a tree for every single letter. And this is one way to do it in one pass. And this isn't the most efficient way. In fact, when we get into the algorithm, you'll see that we have to balance some weights and things like that. But this is kind of motivating the fact that there is a way to do this adaptively. And I think, at least for me, it was important to think about this first on my own and think of how I would do it. And then after that, looking into other people's algorithms. This, in and of itself, I had a fantastic teacher for my Huffman encoding. Again, it was all analytically, but when I did it, it was super fun. And I'm hoping this will be fun too. The problem is, I've never actually implemented this numerically, as sad as that might sound. So first thing we need to do is create a binary tree. Because we're going to be doing visualization, I need to do this in C++ because I want to be using the same subroutine stuff that I've been using before. So there's a lot of stuff there that we need to work through. I guess at this point, I've covered everything I kind of want to cover. We've discussed Huffman encoding, we've discussed adaptive Huffman encoding, so now it's just a matter of doing the visualization, or doing the actual code. So I think, sorry about that. I think everything's ready. Let's go ahead and get started. So we're going to CD into projects. Yeah, there's the visualization stuff I have been using. So the stuff that I did, this stuff. Let me do ocular subroutine. .png. The subroutine webcomic stuff, where I did the drawing here. I want to be using the same thing for this stuff. So I have some ideas of how to do that. Because I think, in this case, it's going to be great to procedurally generate everything. I have a couple ideas of how to make it look really good if we can get the visualization right. So we'll see how it looks. Besides, it has to be data visualization, right? I mean, it's not like I'm going to be able to do actual drawings of this in any way. So let's go ahead and CD back into Simuleos. Oops, forgot that. Simuleos. Okay, now we're going to create a new directory. Make directory Huffman. Okay, and we're going to go over here and CD into projects, Simuleos Huffman. Okay, so the first thing we need to do with the Huffman algorithm or whatever, let's go ahead and make a new file, and the new file is going to be, I'm just going to call it Huffman for now. We can change it whatever we want, whenever we want. We're going to have Huffman, and then later we're going to have adaptive Huffman. So let me go here. Oh, sorry about that. And let me touch Huffman. And then also, if I can spell touch, adaptive Huffman. Actually, maybe I should just call it Vitter. Yeah, Vitter seems fine to me. So vitter.cpp. So now we're going to go into Huffman. Oh, oops. I mean, I'm not in Huffman. My bad. I'm a CP, actually I'm going to move Huffman.cpp. Yep. Yep. There's going to be a lot of that. Vitter .cpp here. Yeah, touch is one of those commands. Like every time I teach people terminal stuff and I have to go through the touch command, it is so hard to teach them the touch command because I'm always like, okay, so let's just touch a file. And then I'm like, what should the file name be? I don't know, heart, touch someone's heart. That's pretty cool. Touch people, touch things. I don't know. It's just, the touch command is kind of a funny command. Okay, so now let's go into Huffman.cpp. I'm gonna start it like I always do. just so I know what I'm doing with my life. Let's go here. Here we are. Huffman.cpp. Okay, so what I'm gonna do, one second. I needed to move my my lab notebook a little bit. By the way, guys, in case you didn't know, I do have a lab notebook specifically for this channel and my YouTube channel now. I've actually gotten quite far in the lab notebook. I've only had it a couple weeks, and I'm like 17 pages in, and they're pretty full. So hopefully this will turn out okay. So let's go here, and let's go ahead and start this file up. So next, purpose. This file will create a simple Huffman tree given a, I guess, frequency or a likelihood of receiving certain letters. Okay, so now we're going to go down here. I have no notes so far, so let's go down here. I don't think we're going to need very much here because all we need is a binary tree. And unless I'm wrong, there aren't any really good, or rather, it is easier to write your own binary tree for this. And honestly, it's a practice I'd like to do because, again, as I've said before, I've never done Huffman encoding numerically before. I've never done it in code. So I would really like to just take some time out and encode up a binary tree, just because I've done that before once, but it's been so long, I feel like I'm a little bit rusty at it. So I'd like to get through and see if I can do that, and then we'll go from there. The binary tree will take most of today, and then the Huffman encoding shouldn't take too long once we have the binary tree completed. So let's go here, and let's do, as we always do, include iostream. And then we're going to int main. Okay, so let's go ahead and think about what we're gonna need here. So the first thing we need to do is create the binary tree. So let's go here and say we need to create the binary tree. Okay, so this is going to be in some sort of class or something like that. And I think it should be in a class because we should have a couple of different functions in here. We should have, I believe, insert, remove, and destroy like the entire tree. So maybe also a search function or something like that. Yeah, so let's go ahead and create things that we're going to need. So the first thing we're going to need, let me think. I think we're going to have to define the node first. So let's go ahead and do, I have some notes over here on the side of how I think it, or how I think it should be implemented. But these were kind of handwritten, so it could be that these are not necessarily the best way to do it. So if you guys have ideas as I'm going through and you think that I'm doing something in a stupid way, let me know, because again, my background's not computer science, it's physics. And so if I do something stupid, it's because I don't really have a formal computer science training. So let's go ahead and create a struct for the node itself. And this is going to be, let me see, we're going to need a couple things in here. We're going to need an integer, which is the key, or rather the node number. So I guess key is okay. And then we're going to need, for this particular case, though not in general, we're going to need a link to, or rather we're going to need a double value, and that's going to be called weight. And I'm going to go through exactly what the difference between key and weight is when we get into the Huffman algorithm. Okay, so the next thing we need is a pointer to the other guys, the other nodes. So we need a node left, and then we need node right, and then finally we need node parent. Okay, so again, the idea is that we keep track of the leaf itself, or the node itself, and whatever's to the left, right, and up. And this will allow us to kind of go through the entire tree. Now, let's go through, I'll store a character as the key, then you can get the decoding automatically. Let me think. Yeah, we could do it that way. So let's see, I think it's just char. I don't think we're gonna need many of them. I think we only need one. Okay, so struct node written. Next, what do we need? We now need a class for the binary tree. So class binary tree. So I guess I'll just call this Binary by tree? No, I don't like that. How about B tree? Something like this. Okay. So we're gonna need a couple things in here. Public. We're going to need a function that does a couple of different things. So we need one. You just keep it in a struct instead of the class. I don't know how to do that. I was thinking what I wanted to do. Can we add functions to a struct? I wanted to add a couple different functions to this struct. So I wanted to do, you know, I wanted to do. Oh, okay. Let me think. What would I have to... I wrote some things I wanted to do in private, but I think they're all the same. Yeah, I guess you're right. We might not need a class for this. So let's try it with a struct. Okay, so what do we need? We need a few different things. So we need a function that is that will create a binary tree. So let's do void B tree binary. How about I just do this? We're gonna do void insert. Oh, 1 second. And we're going to need the letter to insert, so character key. And then we're also going to need, let's see. You can use a private. Oh, interesting. Okay. So let me think here. 1 second, I need some water. Okay. So we're gonna need the character for the key. Oh, okay. Well, that's good to know then. Thanks, Gustorn. I usually just don't do public or private inside of a struct. Okay. So what do we have here? We have void insert, and we're going to need the character key. So that's what I want to be public. Then I need to put a semicolon there, and I'm going to also need a couple of other guys. So we want void. Actually, this is going to be node search. And we want again the character key. And then the last one we need is the void destroy tree, which is going to need absolutely nothing. We just destroyed the tree. Okay, what else do we need? According to my stuff, I think I'm going to need a function to initialize the tree, but we're going to get to that in a bit. So next we need to do private. And let's go into detail with what these guys are. So first of all, the destroy tree command, I think, is also going to read in, let me think. Actually, this might not be all we need. Maybe we just need 3 functions, insert, search, and destroy tree. I guess we also need an initial node. Yeah, I guess we need an initial node. And then we'll go from there. You should rename destroy T to B tree. Then it automatically destroys it on scope exit. Okay. Sure. So you want me to do this then, I guess. B tree. B tree. Something like this. So what does this mean? You should rename the destroy tree command to B tree. Then automatically... So how would I call the destroy tree command if it is tilde B tree? I have not used that notation before. So my guess would be, no, maybe I don't need this top one. Maybe it's just this guy. And let's go here. Destroys tree on exit. Okay. Oh, I see. So it just... Okay. Okay. That should be fine. Okay, so we need insert, we need search. What else do we need? We also probably need the tree itself. So let's go down here. We have the node, which is the character key, double weight, left and right. So let's go ahead and start with an initial node, and that node is going to be the root. And that, I think, is all we're going to need to start. And then we'll kind of add things in as we go along. So let me go here. And I guess we'll destroy this guy. And we'll see what happens. So the next thing we need to do, and again, guys, if I do something stupid, let me know. So the first thing we need to do is, I guess, do this. So let's go up here. What do I want to do? We're going to say B tree. And let's go down here. And we're going to say B tree. Oh, my bad. Of B tree is going to be, 1 second, defining the root as null. So this is just because it is the root of the tree, and you know, we're going to be defining things after this. Okay. So the next thing we need, I had actually put in a specific destroy tree command, but I guess maybe that's not necessary. So let's move on to the next one. So we're going to do insert. Okay. Okay. Open link. See what we got. Struct btree void test function btree test for I in int I less than 10 I plus plus btree loop test. Loop test is destroyed here. Test is destroyed here. Oh, I see. So it means it doesn't carry through. Let me see, btree test. So it just destroys the data structure. Okay. Okay, good. I think I get it. Thanks. Okay, so now we're going to work on the insert command, and we're going to go step by step. So what we need is the key that we need to insert. Oh, did that one backwards. Jar key. Okay, so let's think about how we need to do this. So first of all, in what I see here, let me think. I wrote down a weird, tricky thing, and I'm not sure why I did. So I have two different insert commands and two different, let me see, search commands and stuff like that, where I have one that's public and one that's private. The private one also requires a node that is a leaf to work with. So if we're going to insert, oh, you know why? I think I know why I did this. Yeah, I think I do. Okay, so here's what I'm going to do. I'm going to create an additional private function. You could always destroy the data structure after the point where you couldn't use it anyway. Yeah, I guess that's fair enough. Okay, so what I'm going to do is I'm going to run up here. We have the node root, but I think what I want to do is make that one private. So we're going to do private. And I think this will make sense in a bit. So let's go down here and let's do, what do I want? I want void insert. And then I'm going to do char key. And I'm also going to do node star leaf. Now we're going to do node search. 1 second. And then we want char key and also node leaf. Okay. So, and the reason I'm doing this is so that we have something that we can call that only requires the key itself, which is easier for the user to see, but I think it's okay. I love Twitch 1411. At this point, we're making a simple Huffman encoding algorithm. It's going to be as simple as we can possibly do, just because I don't want to get too complicated with this. Right now, we're doing a binary tree for it, and then we'll kind of work from there. Then what I want to do after that is do some visualization, create basically a Huffman forest, which is why it's called a Huffman forest. But I want to make sure it looks good, you know, because I don't know, like, this might sound really weird, but my last YouTube video was like kind of successful, and I feel like I don't want to lose all the subscribers I just got with a video that they don't like, you know. And so I kind of want to make sure that all the visualizations I do from now on are like really, first of all, visually compelling, and second of all, actually provide information to the user. with how it works and things like that. So I have an idea of how to do that with this Huffman encoding algorithm, which again isn't a very difficult algorithm, but adaptive Huffman encoding is. And so I wanted to kind of do adaptive Huffman encoding in a way that kind of makes sense. But I think I'm going to have to split it up into 2 different videos. I think I'm going to have to do a Huffman encoding one, and then have a to be continued, and then an adaptive Huffman encoding after that, I think. I don't know, we'll see how it goes. I don't want my videos to be longer than 4 or 5 minutes. I think that's how long I want them to be. Anyway, so we're going to have B-Tree Null. Feedback on Reddit about your video was really amazing. Oh yeah, I thought it was quite good. I don't know who posted it on R Physics. That was not me. No, it's okay, Gaston. Don't worry about it. The thing is, as I've mentioned before, even today, I've got like a Twitch group and I've got a YouTube group. My YouTube group is just slightly bigger than my Twitch group, but it's about the same, right? They're both about 600 something subscribers. Actually, I think my YouTube channel just hit 700, but they're about the same order of magnitude, so it should be fine. Ideally, I'd have like a super popular YouTube channel and then kind of like a moderately popular Twitch channel, so that I get a whole bunch of people, or rather, I don't want Twitch to grow to the point that I cannot follow chat, you know? So I don't want it to be that I have like, you know, 100 or 200 people watching and like everyone's talking and I can't get anything done, you know? I use structs instead of classes, and you actually capitalize on struct names. So my opinion, and this might be different than Gustron's opinion, my opinion is that I typically use structs whenever I'm holding just data. And I use classes whenever I'm using datas and, or whenever I'm using data and also functions. However, you know, Gustron suggested to use a struct, and sure, we'll use a struct instead. In the end, it doesn't really matter. As Gustron said earlier, in fact, he said it right here. Let me see, and I didn't even know this. You can put functions inside of structs. And he said the only difference is that structs are automatically public, and classes are automatically private. And so the difference is just that, you know. So let me go here. Good. Okay. So now we're going to work with the insert command, and I'm going to want char key, and then I also want node leaf. Okay, oop. That's me being stupid. That is also me being stupid. Okay. So let's go through here and see what we need to do. So, first we need to do check to see. 1 second. Check to see. Nowadays I use structs because it spares when public modifier. Yeah, I mean, I agree with Gustron. I always put public up front anyway. I think most people do. I think the difference is that, let me think. It depends on how you learned, right? So a lot of people learned with Java and other languages that use a lot of classes, and other people learned with C, which has a lot of structs. So I think it just depends on how you learned. So check to see if the current key, let me think. So here's what I'm thinking. The way I did this, the way I set this all up, let me see. The way I set this all up, I had intended to have the key as an integer. So I have this phrase that says if the key is less than the leaf value, we go from there. However, I have an additional guy here, which is the weight. And I think in the end, I'm going to use the weight instead of the key. You should pass the weight too. Yeah, so it's all held within the struct node, so I think this should be fine. Check to check weights. 1 second. Okay. So what are we gonna do? First thing we need to do is we need to check to see if the current. Oh yeah. You're right. In fact. Yeah, because in the end we're going to be initializing it. Wait a minute. Yeah, well, we're always going to know the weight. So it will be double weight. There we go. You're right. We're good. Yeah, you're right. I wasn't thinking about it. Okay, so now we're going to say if weight. Oh, wow. What am I doing there? Weight is less than. Now let's see. We have the leaf that we're adding in, right? So let me think. We did insert. And oh, here, let's no, it's okay, Gustorn. It always kills everyone. Initialization of tree. Tree with null root. And then we're going to go down here and inserting, what is it? Let's see, node into, what do we want? Tree. Okay. So I have here written down, is it the thing I'm actually inserting? Let me think. So in the end, yeah, so that's what I was intending to do. So in the end, I want them to have an insert command that has the weight and also the character key. So double weight. And then I wanted to see, oh, that was not what I meant to do. That was also not what I meant to do. Weight. And then what do we want? Insert character key. Yes. Double weight. And so then I think I wanted to have the node leaf that I see, but they don't necessarily see. That's going to be added in. But we'll see how it goes. Maybe I'm wrong here. So what I've written down, and I wrote this down a few days ago, or last night, and it was kind of late, and so I might have just done something really stupid here. So I have if key is less than leaf key value. If leaf, let me see. I might actually be doing this the other way around. Yeah, I always misspell weight. Did I do it again? Let me see, checking weights. Wait, I did, thank you. You don't need the key and weight private functions then? Let me see. The node will contain it anyway. Let me see. I don't need the private functions. The node will contain it anyway. So private node, void insert, character key, double weight, node leaf, character key, node leaf. You're saying I don't need key, weight, and private functions then? Oh yeah, maybe you're right. What was I thinking about with the insert command then? Let me think. So the insert command was supposed to, wait, let me check to see what I wrote with the other insert command, the one that they see. So we see insert, if root is not equal to null, insert key root. Yeah, Gustorn, yeah, knows way more than I do actually. Then we do root equals new name. Oh, that's B tree. I want what they see, which is search. So I say if leaf is not equal to null, if key equals leaf, key value return leaf, and then return search. Oh, that's for search. Where is insert? Where is what they actually see with insert? Node B tree, search, void destroy tree, insert. This is the one that they see. So for some reason, I think I screwed this up. Void B tree insert int key. That's what I have written down. So they insert just the key. And they say if root is not equal to null, we insert key root. Else root equals new name. Huh. Okay, so let's see, what do we have here? Let's go through and try to fix this up, because I think I screwed something up. So, I think you're right, Gustorn. The way I have it currently written, we don't need the node leaf. We should just be able to go through the tree. Which it seems weird to me, because I feel like when I did it last night, I thought I needed it. So let me go through and see what I need to do here. I might just take up, maybe I should follow someone else's binary tree configuration, because I feel like binary trees are like a super easy data structure that I should be able to put in pretty easily. Man, this is me not knowing what I'm doing. Okay. But you're right, in this current configuration, we shouldn't need the leaf for this one. Okay, so we have the weight. And then all we have to do is go through the tree, right? And we have to insert what we need to insert with the tree. So I guess what we do is we start with, yeah, except for the fact that I don't know what I'm doing. Okay, so let me think here. Let's go through. I'm actually going to draw this out. Page, new page before. Dang it. Okay. Where's my pen? There's my pen. Dropped it. Okay, so here's what we need. We're doing a binary tree. Yeah, I know. I'm trying to figure this out right now. I feel like I'm screwing something up. So binary tree, that's what we need. What is a binary tree? A binary tree is basically a situation where we have a node up here that is root. And then we have all of the accessory guys here. Now, whatever they are. So these all kind of break off. However you want to break them off. I guess maybe something like this. Doesn't matter. Okay, and we can kind of label these guys as 0, 1, 0, 1. Ah, shoot, I just realized I screwed that up. There, this could be a binary tree. You can only go 1 and 0. So it's usually 0, 1, 0, 1, 0, 1, which is just like the Huffman encoding stuff we did before. Okay, 0, 1. Now, we have a question of what do we need to do here. So for the Huffman encoding scheme, we start the other way around. So we will have all the leaves down here at the bottom. And then we want to successively add parent nodes until we get to the point that we are at the root node. So the idea is subtly different here. Okay, so what we need is a bunch of nodes. We need a way to insert a parent node and connect two lower nodes. So actually what we need to do is find a way to create a parent node and two child nodes. Is that what they're called? Okay, so here's the functions we're going to need. We're going to need insert. We're going to need create, some sort of create tree type of thing. Let me see, what else do we need? Search. Yeah, I guess we're going to need a search function. And then I guess because of the destroy tree thing that Gustron mentioned, we don't need the destroy key. Okay, so let's go through and see if we can do this then. Because I've got a feeling my notes here are not going to work anymore. So, okay, let's see what we got. This might take a while, and actually we might spend the entire day fiddling with this because I don't know what I'm doing. Okay, so you guys are right. With this current iteration, we don't need these guys here. Let's see. So the binary tree, I guess what I'll do is I will continually create more binary trees until we're at the root node. So each binary tree is going to have a root node, and it's also going to have all of the leaves down bottom. And then we'll just kind of start with a single node and kind of add them all together by searching through all the different values and adding in the ones that we need. Okay, so insert, character key, double weight. What we're going to say is we want to add, let's see, these guys to a particular node. So we're going to say the node that we're going to add to is going to be node leaf, I suppose, just like we had before. So what we want to do is we want to add a character key and a double weight to a particular node leaf. Okay, and now we have a question of where are we putting it in this node. So what we need to do is initialize everything. So what we're going to say is, since we're adding it to the node leaf, let me think. We need to say if the weight is less than, let's see, the current weight of the node leaf. Yeah, it should be that. So we're going to say, 1 second, it should be leaf, then we're going to point to the value of key, not key value, weight. Okay. Then we're going to say, we do the following. We're going to say we insert, let me think. And in this case, it should always be this, but I think that's okay. So let's do, wait a minute, is our node, as we have it written down, if we have a left and a right, are these automatically? Yeah, so this is what we're going to say. We're going to say node, sorry about that, insert, then what we want, so we're going to, It's weird notation. I don't know why I wrote it this way, but that's okay. So we're going to say key. What do I want? Yes, I want key. Then I want wait. Then I want the final one, which is going to be leaf left. Okay. So is this okay? Does this make sense? No, it doesn't. Leaf. That I wrote leafed. Let me think. So we want to insert it into the left. So let's just go ahead and assign all those values. Okay. I had a couple else statements in here saying if the key value is less than leaf value. Hey Slayer Darth, what's up? So if leaf left equals null, insert. Yeah. Oh, I see what I'm doing. Okay. Okay. This is just shorthand notation. What I need to do is if... How do I put this? So if there isn't anything to the left, we now need to put it into the left. So if I'm not mistaken, what I need to do here... Wait, is the physicist's favorite clothing brand Calvin Klein? Lord Kelvin. Okay, what do we have here? Weight less than leaf weight. Okay. Which it should always be, again, because we're always inserting here. Let me see. So now what we need to do is the following. So then we say if, what do we want? Leaf left is not equal to null. Then we do the following. Now let me think. I think I'm doing something stupid here. What I need to do is check to see if there isn't a left node. So this would be saying corner? I feel like, has anyone here ever watched Top Gear? The old Top Gear with the 3 original hosts. There was one where they made their own ambulances, and it was absolutely hilarious. Now, I felt bad, because, like, they killed the guy every single time, but it was pretty funny. They had some pretty good ambulances. One of the guys built a car based off of a hearse, you know, like the mortician's car or whatever that you carry the body in. I thought it was great. They made an ambulance out of it. Anyway, it was good. Also ejected incredibly quickly. Like the guy would die from the sheer shock of being ejected that quickly. Okay, so what do? Here's what I'm gonna do. I'm gonna say if it is less than leaf weight. 1 second. Inserting. So we will create, let's think about how we're going to do this. So with the Huffman tree, we're going to start with all base nodes, right? So these are all going to be basic nodes, right? And we're then going to initialize a new, let me think. We're then going to initialize. I'm actually not much of a car enthusiast, but I like Top Gear. It's one of those few things that every once in a while it gets me, you know? It's just, I don't know. I also like a whole bunch of weird things, you know? So like, let me think. Never mind. I'm not going to say weird things I like on stream. That's probably not a good idea. Besides, I can't think of anything right now. Besides programming. Okay, we need a way to insert things either to the left or to the right. So we need a way to check to see if there is actually data in the left or the right. So here we're saying if the leaf to the left is not equal to null, which means there is something in the left. And let's do this. So we have a leaf right and we have a leaf left. We also have a leaf parent. So what we need to do is have a way with the insert command to add something to the left, or if it's already to the left. I'm getting confused here. This is why I wrote it down last night, and I'm really bad at this kind of stuff. Sorry about taking so long with this, guys. So here's what we're gonna do. We have a node. The node has a parent, has a left, and has a right. Is this correct? Let me think. No, I think the node itself is either a parent, a left, or a right node. If this is a non-active version, your tree should get these nodes from lowest to highest frequency, right? Should, yeah. Yeah, that should be true. Let me think. So if we are, if we are here, basically we need a way to add parent nodes. So let's say we have a node, okay? So we have this binary tree. We're going from here to here to here to here. Okay, something like this, whatever. Doesn't really matter. Okay, what we need to do is take these two guys and go up to this guy up here. So this guy is going to have something to the left, and it's going to have something, a parent, but it's not going to have a right. This one's going to have a right, and it's going to have a parent. This guy's going to have a left and a parent. This guy's going to have a left and a parent. Okay, so, okay, if we're inserting, so if we use insert, and we're inserting it to this guy right here, this node, okay, then we're going to check the value. And if the weight that we are currently putting in is larger than the weight that we're inserting, then it's going to insert it as a parent. If the weight is less, then it's going to insert it as a child. Yeah, you're right. So we need a function. I guess it's a function like combine or something like that. Even if we don't go for the simple algorithm, we're still going to need that function. So let's add the function combine, which basically takes in two nodes. And then let me think, what else do we need? We have that function combine. Then, do we actually need anything else besides combine? Let's see, we have combine. Yeah, because we're going bottom up instead of top down. We might want to do it that way. Yeah, so let's try that. Okay, so here's what we're gonna do. Let's go here. Oh, here. Let's go up here and let's just see what we got. So let's go here and let's say we have void combine. Okay, so how's this gonna work? What we would need to do is initialize the binary tree, and then also initialize a bunch of nodes to the binary tree. Then we need to combine all the different nodes. So here what we're going to say is we want node leaf, and we can make this super easy on ourselves by forcibly telling this guy which one's on the left and which one's on the right, which we'll know from the algorithm. However, I feel like it's easier just to do leaf 1, or rather, it makes a little bit more sense to do leaf 1 and leaf node leaf 2. Okay, so we're going to read in two different nodes here for the combine function. Let's go down here. Oh, sorry about that. You'll need the list of character frequency pairs. Yeah, we actually probably don't even need a tree for this. Let me think. We could just do the list of character frequency pairs like you said. But let me think. Why did I want the tree? In the end, for the adaptive algorithm, what are we going to need? We're probably going to need... I feel like we're going to need a tree when we do the adaptive algorithm later on. And so I feel like we should probably have a tree. Let me see. I mean, you'll need the list of character frequency pairs. Yeah, so the character and frequency pairs come in the key and the weight. So the key is going to be the character, the frequency is going to be the weight. Then we just keep track of the left, right, and parent nodes. So here we're going to say creating parent node. Okay, let's go up here. Oh, sorry about that. Oh, that was not what I meant to do. That's what I meant to do. That's what I meant to do. Okay, insert. I don't think we're going to need insert for this one. So is there any case that I could think of where we're going to have to insert retroactively? There is actually with the adaptive case. So let me think. With this one, we're going to have char key double weight. And yes, so this is going to be complicated for the adaptive case. But for the simple case, I don't think it's going to be that bad. Let's see, for the insert command, let's see. We'll probably also need the search command, but for now, we could probably leave without it. So let's just work with the... One second. Let's just work with the insert... No, let's just work with the combine command for now. Because that one's easy. Okay, what are we going to do? We're going to read in the 2 leaves and go from there. I don't think it's a good idea to combine the data structures to the simple and adaptive cases. Really? I mean, in the end, it's going to be a binary tree either way. Besides, what I need is something to visualize. Like, in the end, I need to be able to read in the struct B tree and output a visualization of that. So that later on when I do the adaptive case, it's literally just reading in each binary tree. You can do the visualization by recreating the tree on every iteration. I see what you're saying. One second, let me think. You can do the visualization by recreating the tree on every iteration. So if I had in the struct B tree, one second, let me think. What I need is, well, then I need a function in B tree, which goes through, and it says, let me see. Let me go here. Function to create B tree. And this would be, I mean, I guess from list. So then it'd have to be, we'd need, let me think. We need character and we need frequency. Then what we need to do is put these guys into the appropriate tree. So let me think. I guess it would be create just something simple, tree. And then we would need a vector of, let's go up here. Yeah, no, I'm thinking of how to do that. I'm not exactly sure. So let's go vector. I don't actually see how to do that. So the thing is, I don't understand why I would want to do that in the case that, it's like, to me, the Huffman algorithm's like super simple and just falls out of the binary tree, right? So if we create the tree, everything's set, you know? The trick in the Huffman algorithm is creating the tree to begin with, right? Which isn't so bad. So all we'd have to do is create an algorithm that manipulates this binary tree that we're creating, right? I don't understand why I'd want a separate data structure for this. I think the thing I'm trying to figure out is why you think, or why you say that we need a simple, or a different data structure for the simple and adaptive cases. Okay, so let's go here. And I guess we need a std vector of, I guess, keys and weights. Let me think. There's a way to do pairs in C++, I think. One second, let's go over here. Pairs in C++. Pair. Pair. I've never actually used a pair before. Pair swap, tuple pair, tuple size, make pair. Is it worth it? Why don't we just do 2 separate vectors? I feel like that's easier. Constructor. Is a pair worth it? That's the question. Okay. So we have utility is what we need to read in. Then is that in the simple case, you can create the tree without ever reassigning the leaves. For the adaptive case, you'll likely have to move those around. Let me think. So for the adaptive case, let me see. We're going to start with basically a tree with a single node. And that node is going to be like to the left. And then we're going to have stuff that has not been translated yet. So then we move on to the next one. Oh, I see what you're saying. Yeah. I get you now. The adaptive Huffman tree goes from the top down in a way. So we always build from the root node. But the, let me think. The non-adaptive case does not necessarily build, or always builds from the bottom up. So it builds from the leaves to the trunk. Okay, I see what you're saying. That's fair enough. Okay, so here's what I'm going to do. I'm going to go here. And what we want is just something from simple tree. From, how do I put this? Simple Huffman case. Okay, so we're going to say vector, and what we need is weights. And then we want std. And this is just a simple way. We can fix this later. Vector of what do we want? Wait, why did I put weight? We want double. Or character, I guess. And then we want double. Okay, that's a simple way to do it. We have keys, we have weights. That's okay. So what we'll do is we'll work on this a little bit later. And then we'll kind of go from there. So for now, I think Gustron's probably right. We can probably just work on a simple case. So let's go up here and change this to vitter.cpp, which is what we'll be using for the adaptive Huffman case. And add in an extra dash there. And for now, I'm going to just go down here and say note. Oops, sorry about that. What was that? Binary tree not implemented yet. Okay. Now we're going to go to, let me see, CP, Huffman, into vitter. Now let's see. Imagine you get probabilities 0.5, 0.5, 0.125, and 0.0625. And if you get all the A's and all the C's first, then you have to rearrange the tree, which you don't have to do in the simple case. Let me see. You get all the A's and the C's first. Yeah, you're totally right. And I agree with what you're saying. So with the more complicated case, we have a lot more to manipulate with the tree. And so I guess you're right. So let's just go through the simple Huffman. So let's go in VI Huffman. Actually, let's go into vitter first. And let's change this, create a simple Huffman and adaptive. Okay, now let's go here and let's do VI Huffman. Okay, now we're gonna go down here and let's just do this case here. Okay, so let's go here and let's think about what we need. So first of all, because we are doing the simple case, we don't need so many different functions here. We need, let's see, we need a list of weights. We need a list of keys, and then we need, what else do we need? I suppose, what do we need? I think that node class would have been nice. That node structure would have been nice. Because what I also need to do is keep track of the binary representations of each of the A, B, C, D, and E, and all that kind of stuff. So we need to find a way to go back through the tree in the end, right? So again, with the Huffman algorithm, you end up with these things that are kind of like this. Here. So you have like, oh, let's go up a little bit. maybe something like this. So you have this, and then you have to read back through for 0, 0, 0. One advantage of the pair is that you can sort it and use priority queue for it. Okay, so let me think here. We want... so if we have a vector of pairs, yeah, I think I'm still going to need node. So let's go here. And let's quit. Now let's go into Huffman again. Oh, sorry about that. In this case, we're just going to need a vector of nodes, I think. But we don't necessarily need the binary tree. For this one, I don't think. Yeah, I think we just need the nodes. Okay, so we have the node class. It has left, right, and parent. And now we're just going to need a vector of nodes to work with. And with this vector of nodes, we can do this in a super easy way or a super complicated way. I'm going to do it the super easy way so we can get it done, and then we'll worry about the super complicated way a little bit later. So let's go down here and say vector. Oh, sorry, I need an std of node. And we're going to say this is going to be called... No, I'm not. I'm in the right file. I just had this misnamed. Yeah, so vi huffman.cpp. I just had it, again, misnamed. So I think Vitter and Huffman are like literally the same thing right now. Diff Vitter and Huffman. Oh, diff not found. Yeah, so just except for that right now. So let's go into vi Huffman. Good. Okay, so let's go down here. We need the node, but I think we can remove everything else. And then we'll worry about the adaptive stuff later, as I said. Okay, so what do we need? We need a vector of nodes. Yeah, I keep the file header in there so that when people look at the code, they know, oh, I'm in the right file. And then on stream, I screwed up. The vector node, what do I want? We're going to call this, I'm just going to call it Huffman. Because I don't think I'm going to need very much more than this. Oh, if I can spell Huffman. Jeez. What do I need to read in? I think I'm just going to have to read in a list of all the frequencies that we start with. And then we're going to output a vector of all the nodes. So, wait, does this make sense? If we have a single node... we could go in with all of the initial nodes. So let me think. So how about we do std vector node initial nodes? Okay, let's think. So in the end, we'll have like an A, and we have to go from A to the source in order to find what we're representing this as, right? And so... what should I call it? We're going to need another function then, which is going to be encode. So let's see, what do we want? Is there a way? Yeah, that's what I'm thinking. So we'll do std vector node, and then we want to call this initial nodes. Okay. And then we need another one, which is going to be... that's fine. Don't worry about it, Gustorm. Okay, so now we're going to need one more thing. So this is going to be the guy that does the actual... creates the simple binary tree. And then down here we're going to say does the actual encoding. Okay. Now we're going to say std vector. Wait, no. What do I want? What I want is a whole bunch of binary 1-0s and stuff like that. Does this mean I need a string? Let me think. Binary strings in C++. What's the best way to do this? Changing integer and binary string of digits. Can you safely use for binary data? Manipulating binary strings. I just want 1s and 0s. That's all I want. Just a list of 1s and 0s. Basic string, unsigned character. What do we have? Unsigned character, constant S. Nope. Program, add 2 bits to a string, changing integer and binary strings of digits. Okay, so what do we have? String binary is equal to... So is everyone else just using a string? Just an actual string for binary digits. Include bit set. std string s is std bit set 64 1 2 3 4 5 to string. Okay, 1 second. std cout bit set 64. What is this actually doing? We have include bit set. Std string s is bit set. I don't know what I don't know what bit set is. That was an incredibly useless answer. Yep. Go ahead, give me a link that doesn't work. Let me see. I just want... Yeah, that's what I thought. I wanted another way to do the binary strings. So let me see. What do we have here? Set, byte ID, size of, byte ID set, C++ language considerations. No. Convert hex string to binary string, convert binary string to hex string, binary string to ASCII value conversion. I just want to see what data type you're using for binary strings. Is it bit set? This stores 1 bit as 1 bit. Let's do bit set. Example, C++. Okay, bit set. Let's see, what do we have here? Bit set 16 foo. Let's see, bar, baz. So foo. Okay, that's fair enough. Yeah. Thanks. So we're gonna do here, and we're gonna say include bit set. Okay. So what do we need? Oh, sorry about that, guys. I did not mean to knock the microphone, but I totally did. So what we need then is a vector of, I guess, bit sets. All of some particular size, I suppose. But the thing is, the size here is going to vary dynamically depending on what we read in. So let me think here. Can I create... Let me play around with this bit set stuff real quick. Let me open up a new file, and we're going to call bitset check.cpp. I'm not going to worry about all the stuff, so we're going to do include iostream. And I realize I'm inconsistent with the spacing there. Include bitset. And now we're going to go down here, int main. And here's what we want to try. We want to try the following. So we're going to say bit set of 16. And I just want to try a couple of different things. So std bit set of 16. And we're going to call it bit val. Okay. I want to say, let me see. Okay, so I can set it. You can only set static sizes. Okay. So then what do we do in that case? Well, we can std vector bit set. We will already have the Huffman tree at that point. So with the Huffman tree, we should have a way to find the length from the Huffman tree. So let's go ahead and do vector bit set. And we want bit set to be of size . Let me see. Is there another way to do it? Because if there's another way to do it, I'm all ears here. I just want to... Yeah, it could. Well, no, not necessarily. If we just have them all set to 8 characters long or whatever, and then we truncate the bit values that we have, that's probably fine. It's not going to be that big of a deal. Because in the end... Sorry for the yawn, guys. In the end, if we have like 4 zeros before a 1, right? And then 4 zeros before another 1, we're reading the entire string. So I think that's okay. The question is, how do I know how long this has to be? the length should depend. I can't truncate it. Can I read something out? Here, let me try something. Wait, let me try something. Okay, let's go here. And I'm gonna say bitval. How did they do it over here? Let's do this. PD. And let's make it 8 instead of 16. Let's go here. And let's say std string. I guess we also have to read in include string. Let's go here, std string. Oops, sorry about that, guys. We're gonna do std string, and then we want to read in the following values. So it's 8 bits long, so let's do 0, 1, 0, 1, 1, 0, 1. That is 0. That should be 8. Okay, so this should set that. Now we want to do. I want to try something. I want to read out std cout bitval of 2. So let's do g++, bitset, check. Okay, I expected a parentheses before the semicolon. Fair enough. Okay, so it seems like if you want to be efficient, here's what I would do. Struct Huffman CP, bitset large val code int length. Huffman copy, I guess. If you want to be efficient, here's what I would do. Struct Huffman copy, bitset large value code int length. Let me think. Bitset large value code. Okay, that's fine. That's the int length. A Huffman code point. Okay, wait, let me think. Int length. What is int length in this case? I'm not sure. Is this a length along the Huffman tree that we're at? So you're creating a struct that is a Huffman tree with some sort of bit set value in it. You need the length because you don't know where the code ends without it. Yeah. Yeah, so I was thinking about something very similar. My question, though, is why it needs to be in its own struct? Let me think. Int length, bitset large value code, int length. Let me think. So we have, again, CP, I'm not sure what the CP stands for. Oh, code point. You said code point. We're good. Bitset large value code, int length. Okay. So, okay, so I think you can easily return it. Oh, I see what you're saying. I was going to do it this way. So I was going to do actually the very same thing that you were going to do, except in this case I was going to set this to a large value, return the vector of bit sets, and then I was going to create a separate function down here. And the separate function down here reads in the length, right? So this would say like in the actual encoding, the length of the number of bits. Yeah, so I see what you're saying. What I was going to do was kind of the other way around. So we have vector of bit sets that we return back, and then after the vector of bit sets are returned back, we have a separate function down here that does the actual like writing to the string. So instead of doing the encoding, creates, let me see here, creates bit code, and then does the encoding. And this would be, your version transverses the tree twice. Let me think. Does it? We have a bit set value. We have a vector. Huffman returns a vector of nodes. Okay, so with the vector of nodes, we have... I don't think so. So what this one would do is all we'd need is void, and then we would do encode, and we would just need to read in here the std vector of bit set 16. Wait, maybe you're right. Maybe it does. Let me think. I'm thinking here. std vector bit set of 16. So read in all this guy. Okay, you're probably right then. So let's go here and let's create a new struct. Struct to hold bit values. And also, what else do we need? Bit values and length. The Huffman tree. Yeah, you're right. You're right. Okay, so what we're going to do here, and we're going to say struct. Guess we're going to call it Huffman code point. Let me think. I guess that's fair enough. Huffman. Let's go here. Huffman code points. Okay, Huffman CP. Let's go down here. We're gonna want here. So we're gonna say bitval std. Sorry about that. What do I want? Std. I think I'm gonna need bit set. Yeah. Of some large value, and so the large value I'm going to set to be 32. It's large enough for anything I could think of. I mean, 16 is probably large enough anything I could think of, but that's okay. Let's go here and say 32 is our arbitrarily set. Okay, so let's go down here, and we're going to say std bit set of 32, and we want this to be called what do we want? I guess code is fine. And then down here we'll say double, oh not double, integer length. 32 is way too small. Under what circumstance would we have, let me think. There's 26 letters in the alphabet. So that means with spaces there's 27. What? Oh, we're doing this completely differently. I wasn't thinking about... I see. Okay. What I was thinking was that... I was thinking this is going to go a little bit differently. Let me think. I'm now incredibly confused. Okay, wait. We just did this. We have A is 1, B is 0, 1, 1. C, I mean, that's 3. 3 max, right? So even if we have all the letters in the alphabet and all caps included there, so it's 26, that's going to be 26 plus an additional, let me think, plus an additional, oh, wait a minute, how are you thinking about doing this? I was going to have a vector of these guys. Oh, wait. So I thought in the end we were doing vector Huffman CP, right? That's what I thought we were going to have. So it's going to be a vector of these guys, right? And then we're going to read the vector into the encode function down here. I mean, why would we need... I don't understand why we'd need more than 32. Like, so let's see. That's 26 plus 26, so that's going to be, let me think. One second. We're going to call this create bits. Okay. I'm going to have to read in the vector of nodes. And we'll call this tree. Why not? And let's go down here. Okay, let me think. Yeah, I was talking about an efficiency standpoint. But wait, I'm trying to figure this out. Are you saying what we need to do is have... One second. Name it something... wait. So we have bit set of 32. Okay, you're right, though. I think 32 is a little bit too small. Let's say 26 times 2 is going to be 52. Then plus 1, so let's say 64. With spaces, parentheses, commas, and everything, I guess 128 is probably fair enough. But I don't understand why we need larger than 128. So you say you're talking about an efficiency standpoint, but I'm not exactly sure here what you mean. So 128 is as large as I could imagine we would need, right? So if we have, let's see, all the numbers 0 to 9. I mean, 128-bit. How many bytes is that? Is this what we typically... I'm not sure. Let's just stick with 128 for now, and we'll worry about it in a bit. So next thing we need to do, because I'm terribly behind here, is we need to go... Oops, we need to go down here. So this guy... One second. Let's pop all these guys down here. In the end, we want main to basically call, I guess just Huffman. That's what we wanted to call. Or I guess maybe create nodes. Yeah, maybe we should have an additional function to create nodes. Function. Oh man, I'm very bad with this naming stuff. Creates nodes. Let's go down here and we're going to say it returns an std vector of nodes. Yeah. Of nodes. And then what do we want? We want create nodes. And we need an std vector of, what do we want? I guess it's going to be weights and keys. So we want char, and then we want std vector of double. I was saying that you could go for 128 because you sacrifice very little performance for a pretty huge gain in maximum code length. Okay, yeah, I mean, that's fair enough. In the end, I guess, yeah, we'll see what happens. Okay, so vector node, create nodes, that should be fine. So we want vector of characters, vector of doubles, from vector of characters and doubles. Okay, so let's go down here and let's just get started because we have spent the entire day, well, kind of messing around with little things. So, but that is how coding goes. So, okay, good. So we have int main here. Let's go ahead and mark that one, just so I know where it is, and then we'll go from there. Okay. Just to make sure I don't have any typos at this point, I'm going to very quickly compile it. Then we'll go from there. Good. Okay, so there's absolutely nothing in the code yet. So let's go ahead and create the nodes. So first of all, we have a std vector of everything we need. So let's go down here and we're going to create our vector of nodes. So we're going to say, in the end, we're going to have to return whatever it is. So let's call it initial nodes. Okay, let's go up here and we're going to say std vector of nodes. And this is going to be, one second, up here. And this is going to be what? Let's see, we have initial nodes of size, oops. That's what I get for being, so let's say keys and weights. Weights. Okay. Sorry, today's been so scattered, guys. Initial tree, vector Huffman CP. So let's go here and change this to bit strings. Why not? Names don't matter. Nothing matters. So we're gonna go here and say keys, and change this to weights. Go down here and change the encoding to have an additional guy, which is bit strings. I realize, yeah, it's probably a little rough, but that's okay. So we're going to return the initial nodes. The initial nodes are going to be of size keys dot size, and seems fine to me. Vector initial nodes. So now all we have to do is go through and initialize each of the nodes. So we're going to say for size t, I equals 0. I less than keys.size. SE vector v reserve size is going to be marginally much faster than SE vector size. Wait, really? Huh. I had no idea. Yeah, we can do that from now on. That's fine. Oop. What is it? It's going to be initial nodes dot reserve size. Yeah, that should be fine. Okay, so initial nodes, I less than keys dot size. Then we're gonna do plus plus I. Go down here, and basically all we're gonna do is, if I can spell initial nodes correctly, is, hey Solipe, how are you? We're gonna go down here and we're gonna say we have our initial nodes. And we're going to go through and add a key and a weight to each of them. So with the initial nodes, what do we want to do? We're going to say initial nodes of I dot key, not hey, key, is going to be equal to key of I. Next, we're going to say initial nodes node of I dot weight is going to be equal to weights of I. Okay. And then we just return the initial nodes, and that should be fine right there. So now here we read in the initial nodes. And what do we do for the Huffman stuff? Well, okay. We now have the list of initial nodes. This is where things get a little bit tricky. Second note, if you reserve, you have to use pushback to add a new element. Wait, what? Let me see something real quick. Right here, go here, G++. Wait, pushback is faster? I thought pushback was always slower. Let me think here. So let's go to, real quickly, let me check this out. Let's go into VI, same thing we were using before, bitset check.cpp. Now let's say bitval. So we're initializing it of a particular size. So let's go here and let's say bit set dot reserve the following. Then we're gonna say, I feel like that's the wrong way to do that. That's totally the wrong way to do that. Reserve SD string. I don't think that's gonna work at all. Yeah, I knew that was gonna break. Let me actually write this up. Just Twitch chat is bad for demonstration. Your eigenvector video is pretty interesting. Can't wait for more videos. Hey Sally, thanks for the compliment there. I will be making new videos, I think, every other week from now on. I realize like my last video was like 7 months ago, but I'm actually working on my next video right now. Well, presumably my next video. I do all of the coding for all my videos on this channel. So if you're interested, and this is the kind of stuff you're interested in, I'm not going to say you're a nerd or anything, but feel free to follow. Because that's kind of the point of this channel, making simulations for no apparent reason. So, but I'm glad you liked the video. Appreciate that. So we're going to do bit set of 8 bitval, reserve. Let's do this. So string is going to be of 8. Oh, bitval is always of 8, of course. What am I doing with my life? Let's go here. let's keep this the same it was before, and let's just mess around with the vectors. There. Good. Next, we're going to say std vector of double, and we're going to call it check. Then we're going to say check dot reserve 8. Okay, it is a size 8. Then we're going to say check of 0 is going to be equal to 4. And let's stdc out 4. Oh, check of 0. End line. Write this, brain quit. Now let's go to g++ bit set. Vector is not a member of std, fair enough. So std vector. Never mind, that wasn't fair enough. What did I do? Check was not declared in the scope. std vector is not a member of std. Oh, ha! I probably forgot to read it in. Yep, it sure did. So include vector. If I can spell vector. Brain quit. G++. Good. A dot out. So it does seem to read out 4. So for the record, I'm not sure. Yeah, okay, for now it will work this way. This will work okay the way it is. And then we'll worry about this in a second. So we add all these guys together. So now the actual Huffman encoding. So like I did at the start of this video, or this episode today, 2 hours ago, whenever, Huffman encoding's not so bad. All we need to do is a whole bunch of searching and sorting. So let's see, we have all the nodes, we have all the weights. We have a sort command based off of, let me think. We have a sort command based off of the check vector.size. Sure. 1 second. vi bitset.cpp check. Let's go to stdc out. Check dot size. End line. Let's do g++. A dot out. A dot out. 4 0. Okay. So vi bitset. How did it know if my check.size is 0? How did it know? Let me try something else. Check of 1 equals 9. And let's output check of 1. Why not? Let's check both of them. Why not? Tab. Check of 1. End line. Brain quit. G++. What did I forget to do? 15. SEC out check. I forgot a semicolon. G++. A dot out. 4 9. Size is still 0. I'm not sure why size is still 0 actually. You overwrite the memory location at check n. So what you're saying is if I don't, doesn't do bound checking. Okay, so what I should have done is check.pushback. 1 second. Four. And check.pushback. What do I want? Pushback 9. So then we're going to do G++. Check. Oop, my bad. I forgot periods. Let's do G++. A dot out. Okay, that's fair enough. So we're going to go here. And we're going to say, let's call it this. Initial nodes dot pushback. And what are we going to call it? We're going to call it node 1. A node, the node, node. Temp node. And we're going to say temp node.key. And temp node.wait. There we go. Temp node.wait waits should work. Right here, let's go up to the last G++ command that compiled the Huffman. temp node. Of course not. And you go up here and define node temp node. Node G++, Huffman.cpp. Good. Well, it's 6:55 in the morning. I have 5 minutes left. Let's see how far we go. Check at 0, 1. It will throw an exception. If you do check at 0. Wait. What does the at command do for the, 1 second. vi, what do we have here? Bitset check. What does the at do for a vector? All right, let's take a look. Open link. What do we have here? SD vector t. Okay. V naught is equal to sets value overriding default one. Allocates the vector and allocates enough memory for n elements. Sure. Pushback adds a new value to the vector. Best solution is C++ 11. Struct node char double weight. Sure. Node equals default. Node character k. Okay, fair enough. Node character k, double w, key k. Oh, I see what you're doing. So you have node equals default. So if we do node v.reserve and place back, character k1 equals a, w1 equals 0.1, v.inplace back, k1 w1. I see. Okay, and you're initializing. Yeah, that's actually quite clever. Okay, that's probably what I'll do. Okay, so we have. I want to keep left, right, and parent there. So let's go here, and we're gonna say node. And you said this equals default, but I don't know exactly what this statement means. Now we're gonna say node of what do we want? We want character key, and oh, that was a car key, character key, and double weight. Okay, and for this we want. How did you write it? Oh, it's literally what I would expect. You can pass the parameters to nplace back as you would type the character's construct. It's not terribly important for this problem, but it's a very cool optimization trick if your type is expensive to copy. Yeah, okay, so let's go here and we're gonna say, yeah, let's do it this way. DD. We're gonna do character K, double W. So now we're gonna say key equals K, and we're gonna say weight equals W. Good. So what's next? We have that all set, and what do we do over here? So reserve n, a vector of nodes v, and we reserve n, and then we say character 1. Okay, so you can pass parameters to nplace back. So how about that then? We try this, write that, and now let's go through and let's write all this out. So we're going to do initial nodes, nplace back is what we want. Back, and then we want to read in keys of I, and then weights of I. Just to check to make sure this works, let's comment this guy out. And what are we going to do? Write this, go over here, write and quit, run this G++ command with Huffman, and then let me test something in main. So where's main? Main is of course up there, right under the main tag. So first we're going to do is create our vector of weights and keys. Okay, so here's what we're going to do. What do I want? So we're going to do vector of keys. Vector, what am I doing? Vector character of keys. Then we're going to do vector double of what do I want? What do I want? What am I doing? Weights. Okay, now let's do vector dot reserve. And I'm going to give it, keys dot reserve. And what do I want to reserve? Let's reserve 5 for each. Weights dot reserve 5. Actually, 5's a lot. Let's just do 2. Now we're going to say keys dot pushback. Actually, wait. Let's do... Yeah, that's fine. Keys dot pushback. We're going to say I. Then we're going to say keys dot pushback. What do we want? We want, let's say, A. Okay, now we're going to say weights dot Yep. This is me not knowing vectors. Equals the following. A, B. Then down here we're going to say weights equals 1, 2. Okay. Now what we're going to do is test this function real quick. So we're going to say create nodes. So we're going to say std vector of nodes, and this is going to be equal to create nodes with keys and also weights. And then at the end we're gonna, yeah, I mean that's fair. I need to learn these anyway. I've been using C++ 11 regularly. Okay, so let's go down and let's do the next one. So what we need to do is, after returning the initial nodes, we'll call it initial nodes. Now let's go down and let's do for, let's say size t, I equals 0. Then we're gonna do I less than, why not, initial nodes, nodes dot size. Then we're gonna do plus plus I. Then we're gonna say std cout. We want initial nodes of I, and then we want key. Then we want a tab. Pop it down here and say initial nodes of I, wait, end line. Write this, go over here, G++ Huffman. What I do, vector character, expected primary profession, ha, std, and std. G++, a.out. What? std bad allocated. Throwing instance of std bad allocated. What did I do? Keys.size, initial nodes.reserve, throwing instance. Let me see. std bad allocator. Let's go down here and let's see. That's 703. Use it in the loop. Print size 2 so you'll see it's correct. Never mind. You use it in the loop. Let me do this. std cout. Here. std cout. I believe we don't get this far, so let's do initial nodes dot size. Yeah, I broke something. End line. Right here, go over here. G++, a.out. So we don't get through here. So let me see. We do node temp nodes. Let's go here and output some things. So we're going to say std cout. What do we want? Let's do keys.size. End line. G++, a.out. Okay, so apparently when we get to this reserve, we're actually in trouble. std cout reserving. End line. G++, a.out. Oh, okay. We are dead before we're even in the water. Let's go here. STD, C out, 1, and line. And then we're going to go down here and say, maybe it's because, I don't know, STD, C out, 2, and line. G++, A dot out. So we get to 1, but we don't get to 2. So we're having trouble initializing the weights in characters here. Okay, so this means let's just initialize these guys differently and not worry about it. Let me see. Initializing a vector with values C++. Pushback 10, constant array. What did I do? Oh, really? Is that what it is? My bad. I didn't know that would make a difference. You're right. Fair enough. This is C++ that we're talking about. Let's go here. DD, write this, go, and over here. G++, A dot out, A1, B2, good. All right, so that's going to be it for today, guys. I think what I need to do is delete some of these SDC outs. SDC out. Now, what are we going to do? So that's going to be it for today. It's 7:06 in the morning, so it's a little bit past the time I typically end the stream. Tomorrow, we're going to finish up the simple Huffman stuff, and then we're going to start visualization on my... Wait, today's my Wednesday. So tomorrow's my Thursday, and we're going to start visualization on my Friday and spend the entire weekend working on the visualization here. If the visualization turns out good, this will be the next YouTube video. If it doesn't turn out well, then we'll spend some time doing other things. I would like, again, to get videos out every other week, and I need to kind of get some stuff, or rather, we have a whole bunch of stuff that we've done before that we can totally do videos on. So I think we have stuff that we could do for the next week, but I would really like to do this Huffman stuff next because I think it's kind of fun. Anyway, guys, let me go ahead and delete these guys. I'm not going to commit this one to GitHub because it's, you know, we don't really have anything yet but a skeleton, so I don't see a reason to commit this to GitHub. When we start doing the adaptive stuff, we're going to have to take this code and revitalize it. But I think what I'm going to do, because this is taking significantly longer than I thought, I'm definitely probably going to split up, I'm definitely going to split up the Huffman and the adaptive Huffman stuff. So we'll do Huffman, wait a little bit, then do the adaptive Huffman stuff. I think they'll both turn out pretty cool if I can get this right. But we have to do animations and a whole bunch of other stuff first, so it's going to be a little bit challenging. Anyway, guys, at this point, I'd like to go ahead and end the stream. So have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you guys next time for the next episode of Simuleos, where we continue working on this Huffman stuff, finishing up the simple case, then working with the adaptive case, probably next week or something like this. This will probably take a full week to do the adaptive stuff and a few days to do the regular Huffman stuff, but a full week if you include the visualizations for the regular Huffman stuff. So this will take a good bit of time. The DMRG stuff is going to be put on hold until I have a better understanding of what exactly we did, but I'm glad we did the diagonalization because that helped a good bit in understanding how things work, I guess. Anyway, guys, thanks again for watching, and I'll see you next time. Bye, guys.